Hello everyone! Today we are going to discuss about algebraic and transcendental numbers. And here is where the story begins. And these are our table of contents. I divided into 4 parts. First, I'm going to talk about a number's tale. Once upon a time, in the magical world of numbers, there was a young number named the square root of 2. And this is the picture of him. He is very cute. He lived on the continent of algebra with his friends, integers like 3, fractions like 1 over 2, and even imaginary numbers like I. And this is the picture of the continent of algebra. Every number on this continent had a special connection. They could trace their roots back to a polynomial equation like this. An(x to the power of n plus 2a0, and the coefficients are all rational numbers. But one day, the square root of 2 heard about numbers living far away on the Transcendental island in the ocean of infinity, and these numbers had no ties to polynomials. Curiously, the square root of 2 set out to learn what made these numbers so different. As the square root of 2 prepared for his journey, he thought about his own roots. I am an algebraic number, he said. I solved the equation. X squared minus 2 equals 0. And he looked around at his friends. The integer 3, who solved x minus 3 equals 0. The fraction 1 over 2, who solves 2x minus 1 equals 0. Even the imaginary numbers I, who solves x squared plus 1 equals 0. We are all connected to our roots, the square root of 2 realized. As the square root of 2 reached the ocean of infinity, he saw the Transcendental Islands, which is the picture of it. And these numbers were unlike anything he'd ever seen. No polynomial equations could connect them back to algebra. They were free, floating in the infinite vastness of mathematics. Take pi, said the wise number. It's the perfect example of transcendental number. It appears everywhere, circles, waves, even quantum physics. But it has no algebraic roots, and they can't be written as the polynomial equation. And don't forget E. I did another number. It governs growth, interest, and nature, but it's as distant from algebra as pi. As the square root of 2 sailed closer, he realized the ocean was vast. I thought transcendental numbers were rare, he whispered. Not at all, said the passing transcendental number. We are everywhere. Algebra may seem big, but it's just a tiny island. Most numbers you will encounter are transcendental. Wait, most numbers? Gasped the square root of 2. Yes, the transcendental number said. Algebra numbers are the expressions. Actually, we are the rule. And so, the square root of 2 returned home with a new understanding. And the second part, we are going to discuss about the magic of transcendental number. The first transcendental number was discovered by French mathematician Joseph Liouville, and he constructed and proved that a specific number is transcendental, reaching the form like this. This number, when written as a decimal, looks like this. Using his method, we can construct a large class of transcendental numbers, and these numbers are called Liouville numbers. Next, there are another interesting number, which is Hilbert number. Look at his picture, and the number may look simple, but it is actually a transcendental number. This was proven using a result called Gilfan theorem, which states that if A is an algebraic number and B is an irrational number, then A to the power of B is transcendental. In the case of cubic number, the 2 is an algebraic number and the square root of 2 is irrational. So by Gilfan theorem, 2 to the power of the square root of 2 must be transcendental. The third part, we are going to discuss about transcendental numbers in everyday life. First, let's play a simple game with numbers. Imagine we take the number 10 and split it into equal parts. For example, we split it into two parts, which is 5 times 5 equals 25. We can also split it into 3, 4 or more parts and multiply the results. What happens then? Let's see. Examples. We split it into 2 parts, 3 parts, to 6 parts, and we look at the results. As we increase the number of parts, the product first grows, which is a maximum when split into 4 parts, and then starts decreasing. Why is this happening? Is there a hidden rule behind this? To find out the mystery, first we're setting up the function. When we split the number 10 into n equal parts, each part is x equals to 10 over n, and the product of all parts, we set up the function Pn, which is equals to x to the power of n. Now we want to figure out, for which n does this product become the biggest? And we simplify using the logarithms to make the math easier. Then we expand it step by step, and we get log in Pn equals to n log in 10 minus n log in n, and this gives us a nice clean function to work with. The next step, we're using the calculus. To find the maximum, we take the derivative of log in Pn with respect to n and get this result. Then, step 4, we solve for n when the derivative is 0. And this gives us n equal to 10 over e. Using the first derivative test, we know the product is biggest when n equals to 10 over e, or roughly 3.68 parts. Why is this important? Here's the cool part. Splitting 10 into 3.68 equal parts isn't practical, but it tells us something amazing. If each part is close to e, the product is maximized. In the case of 10, for n equals to 4, each part is 2.5, and the product is P4 equals to 39.06, which is the largest among all splits. And we know the power of E. Why does E show up there? It's not magic, it's math. E is the most efficient number for balancing size and quantity. It's the same reason E is used in compound interest and natural growth models. Nature just loves E, and now you can too. And the fourth part, we are going to talk about math meets art. Looking at the beautiful picture, it is actually generated using the transcendental numbers, the spiral side. Transcendental numbers like E define the curve's perfect expansion rate, creating a pattern that never overlaps. It remains in perfect harmony. And look the other side, the color gradient side. It features a vibrant gradient created using the digits of pi. Each color corresponded to a digit 0 to 9, forming a unique sequence of shades. These colors might look random, but they are directly derived from pi's infinite, non-repeating decimals. Together, these two representations, the structured spiral of E and the chaotic beauty of pi, show us how transcendental numbers bridge logic and creativity. From galaxies to abstract art, these numbers are everywhere, quietly shaping the world around us. Math, after all, is the ultimate artist. And this is the sample reference I used. Thank you for your listening.